So, buonasera a tutti. Um, you may think that this lecture will be in Italian, but it is not, unfortunately. I have to speak in English. Now, first I want to thank the organizers, especially Saverio, for inviting me to speak at this edition of this festival. He wanted me to talk about chemistry and poetry. And I am very happy to do so. I am a chemist and I am a poet, and I bring the two together in my life. Let's talk first about chemistry. So, there was chemistry always because human beings have been put on this earth to transform it. And so before there were professional chemists, there was always chemistry. Chemistry is the art, craft, and business before it became a science of substances and their transformations. And I want to show you a little evidence of this. So, human beings have craved the color blue. That blue was available to artists when they had patrons who were rich enough to buy for them powdered lapis lazuli, which you see at lower left, from which ultramarine was made. And that is the pigment, for instance, that Giotto used in the Scrovegni chapel. But here you see three masterpieces of ancient art. At left, at the top, a wall painting from Luxor in Thebes. In the middle, the gate of Ishtar, which once stood in Babylon and you can now see in Berlin. And at right, a Hellenistic wall painting which preceded a period of realistic representation that preceded the Italian Renaissance by a mere 1500 years. The blue or the green in all of these is not lapis lazuli. It is an article of commerce of the ancient world, something which the Egyptians were very good at making. It's called Egyptian blue. There's a little powder of it shown here in the bottom. It comes from the Egyptian mastery of glass and faience, and is essentially a glass, which is quartz plus sodium carbonate, with a little bit of a copper pigment that is added for the color. And then it is ground up, and this was sold and was used to make every one of these works of art. Now, there was chemistry being done, for better or for worse, very near you in ancient Sardinia. So the Romans, wherever they went, built baths. They were crazy about bathing. And here you see some of the Roman architecture, but also you see here a bath. This is one at lower left, which is in England, still very well preserved. At upper right, you see some of the pipes, and the pipes were made from lead, piombo. The lead, also the pipes were joined with a lead oxide, redminium. And here are some of the bars of the lead. And this was a major industry in Sardinia. The lead, ore of lead, the main one was galena, a lead sulfide, and this was very easily transformed into metallic lead by a reaction, which you see here, a chemical reaction of lead sulfide with oxygen to give off SO2, lead oxide, and a lead oxide with charcoal, carbon, giving off carbon monoxide. Two not very healthy gases released. This was not a healthy profession. The lead mining and the lead refining. It was the amount of lead produced was immense. The estimates are that over the years, 600,000 tons of lead were made. And one reason was not that the Romans liked to bathe that much, but the lead production also led to silver. There was a little bit of silver, about 1 part in 600, and that was enough to make it valuable to produce it. The amount of lead production is staggering. Here's a recent scientific study, which is rather interesting. In Greenland, people study ice cores. They drill into the ice and take out an ice core, and you can date the rings. There are rings in there from different amounts of precipitation in different years, which you can date the ice. And they analyze that for lead. And here is the graph that you see here. Let's see here. You see here a graph which shows a peak. This is time going back from the present. And from the present, at around 2,500 to 2,000 years ago, there was a gigantic peak in the lead content of the ice due to way pre-industrial pollution of the environment. Some of the lead volatilized and found its way over to Greenland, as far away as Greenland. This correlates very well with historical records of mining. Some of this is described, of course, in Primo Levi's book. Here is Levi as a chemist, as well as a writer. He was a chemist, and rather interesting, a book he did not finish at his death is called The Double Bond. And I will come back a little bit to that. This is a biography of Levi by Carol Anger. In here is what he writes about Sardinia in a chapter about lead. And you can read it better than I can here. He describes the lead mining. It's interesting that also the phrase in another context about the years of lead is used in a totally different sense later. This is a chapter he wrote as a young man, and the last phrase are the end of this chapter. So this is the definition of chemistry. It is substances and their transformations, summarized pretty well by the equation A plus B going with an arrow to C plus D. What matters is both A, B, C, and D, and the arrow is very important. The arrow is the symbol of change. In order to demonstrate this for you, what I would need to do is to do a demonstration right here. And I did not know if the safety committee of this auditorium would allow me to blow something up here. And so I have brought some slides instead. Here you see two substances, a reddish liquid, bromine, beautiful gas above it. At right, aluminum, both first made about 200 years ago. And initially, the aluminum was very, very expensive, so that Napoleon III served his second-rate guests on gold, his first-class guests on aluminum dishes. In 1885, it became as cheap as it is today, an article of commerce that was made possible through some very clever chemistry by two young men, one in the United States, one in France. You put the aluminum into, this is A plus B, okay? You put the two together. Nothing will happen, whether it is between two chemicals or between two people, until you bring them together. And so you put one into the other, and what you get are, you get flames, smoke, foul odors, absolutely everything you expected of chemistry. And at the end, you get something totally different. This is C plus D, which doesn't look like A plus B. This is chemistry. This was always chemistry. And it leads to a certain view of chemistry, this sequence of reactions that I showed you, which leads to a view of chemistry which can be summarized by this. This is a 1942 Walt Disney comic book, and you see what happens here. Donald Duck comes in, the nephews are doing something, he does something stupid, nobody is wearing safety glasses, an explosion happens, the egg upon the head. What always happens in a Donald Duck, I've forgotten the Italian name for Donald Duck, but you can remind me. This is one of the images that follows chemists. It is inevitable, but it is a little bit of a problem, but it has a piece of the truth in it. Of course, what it does not have is that no explosion, no Donald Duck chemistry is ever going to make a profit for you. That is, in either a chemical laboratory, small or big, if you want to make something to sell, you have to make it efficiently, and that is not by doing explosions. That is a wonderful way to waste everything that you have. So that is one interesting thing. Now here I show a bush, corbezzolo, which grows here. And I show it because the chemistry that goes on in those experiments that I showed you is also going on in every living thing. It's often going on too slow or too fast for us to see. For too fast in the reactions of enzymes, too slow in the fruit ripening, but we can see the color change, and there is some chemistry in there. And that is that chemistry is interesting to observe and to think about, because it is, in a way, the beginning of one bond which we perhaps do not think about. And that is that people are bonded to each other by a common chemistry, no matter how they look, no matter where they come from. If a doctor wants to treat them, he knows what to do, or perhaps he doesn't. But he knows that this human being shares a chemistry with another human being. That chemistry is there. Here's an example. It's a molecule I'll come back to for several reasons. Morphine. Anyone in this room who has had a serious operation knows what morphine is good for. It is the gold standard, the first line painkiller in this world. And you also know that the doctor tries to get you off the morphine as soon as they can, because it is addictive. And a derivative of morphine is a deadly addictive drug, heroin. That morphine works on everyone. It is the bond in a way, because we all have, no matter what we look like, no matter where those children come from, we have molecules in us which are affected by that morphine in a way that we want. That common bond extends not only to human beings, one you recognize at left here, but also extends to animals as well. We share with animals a large part of our chemistry, as much as 99% of the processes, even as we are very different. And this is why, of course, you can test drugs on animals. And we share a good part of chemistry even with plants. In fact, we share a large part of our chemistry with everything from single-celled organisms. There are differences. The two animals at the top here exhale carbon dioxide and inhale oxygen and nitrogen, but we use the oxygen. But the plant at the bottom takes in carbon dioxide and in the process of photosynthesis with the aid of sunlight produces oxygen. So there are differences. Okay. In the last 200 years, we have learned to look inside those substances undergoing transformations. And we have learned that inside those substances are atoms. Oh, incidentally, we did not wait for any microscopes to show us that. We did it through indirect experiments using our fallible senses and the extension of our senses, our instruments, and with a lot of clever experimentation and thinking, we found out about those atoms. But more interesting than atoms, we found out that there are persistent groupings of atoms which are called molecules, and so now there is the second definition. That chemistry is the art, science, and business, it always was. Now it's the science as well of molecules and their transformations. A macroscopic view for substances, a microscopic view for molecules, and chemists move very easily between these two worlds. Now, molecules are assemblies of atoms which are held together by bonds, chemical bonds, persistent links. The analogy also to keep in mind is that atoms are the playing blocks, are the Lego blocks. What's really interesting is not the Lego blocks. What's really interesting is what your child does with the Lego blocks. Whether it builds a dinosaur or a castle or a city, that's what's interesting. And there isn't much variety in the building blocks. There's only about 100 elements, but there are now millions of molecules. Chemists have made 70 million molecules in 200 years of frenetic activity, and there's many more that's still to be made. So here are some of these molecules. At the top is carbon dioxide in 3 different representations. There's a chemical formula, there is a model that's built so it fills space. There is a kind of another extended model. There is a chemical formula. And the atoms are not standing still frozen. It's as if they are tied together by springs, so that another representation of the chemical bond is like a spring, and these atoms are vibrating in different ways. For instance, way A here is the central atom is still, and the others are moving like this. And way B, the one atom moves this way, and the other atom moves that way. So it's like this. And the third one is they bend like that. And they're doing everything at the same time, a little of it, or a lot. So if you could see it, it would be vibrating like that. Just the idea that there are several ways to look at a molecule is interesting because here you are, scientists, you could tell me. You guys seem to know what reality is about. So how come you are giving me several representations of reality? There is an underlying reality, but just like in art, we have many representations of it. This is one of the links between science and art. The same kind of molecules occur. That CO2 molecule is emitted by the animal at right as it breathes out and is absorbed by the leaves of the plant at left to make oxygen. That very same molecule we worry about. It's never present in the atmosphere in very great amounts. It's present in the atmosphere typically in only 400 parts per million, less than 1 part per thousand, even though this molecule is essential for communication between plants and animals. It's not there in very large amounts, yet we worry that there is too much of it there. So here are some molecules. And these are molecules that are simply beautiful. They're beautifully simple. They're shaped like platonic solids. Platonic polyhedra, tetrahedron, a cube, a dodecahedron of carbons with hydrogens going out, and at lower right, a molecule which should be on a flag of Italy, a molecule that's shaped like a soccer ball. These molecules are very beautiful. I don't have to tell you they're beautiful. They have a direct line into our soul. And the moment I show them to you, I feel guilty. The reason I feel guilty is I know some other molecules that do not have a direct line into my soul. Here is one with 9,500 atoms, 4,500 hydrogens, 2,500 carbons, about 700 oxygens, 700 nitrogens, 12 sulfurs, and exactly 4 iron atoms. And this molecule, it just doesn't look pretty. It's not simple. And one tries to simplify it by removing all the hydrogens, for instance, and it still looks here in the simplified version like some pasta congealed from primordial soup or a dance of some tapeworms. This molecule I had to be taught to love, and yet it is the most beautiful molecule I know in the world. It's the biochemical molecule that we know more about than any other biochemical molecule. There are 2 chapters about it in any biochemistry text. This is hemoglobin, the oxygen carrier in the blood, by which we take in the oxygen in the lungs and it carries it to our cells. And the oxygen is held at the iron atoms at the center of these 4 green platelets. So the reason I feel guilty is because it's complex, and I don't seem to love it, but it's important. Where is chemistry? Is chemistry in hemoglobin, or is it in those beautiful platonic polyhedra? The answer is that chemistry is there in between. It covers those, but it's very much in the terms of complexity of a molecule like morphine. Here is that same morphine, which is the painkiller. Here is a model of it. The blue is 1 nitrogen, the oxygens are red. Here is a typical chemical structure. And there is a little bit of a trick to reading these, where there is a vertex of a polygon and nothing is written. That means that you have to put a carbon there and sometimes add some hydrogens. But the other atoms are written out. So this is about the level of complexity of the real world. Now, an interesting thing is that I have here going on in my mind, and I try to carry you along here. There is a struggle between simplicity and complexity. This is really aesthetics. This is not chemistry. Why do I like that simple molecule that looks like a polyhedron? Why did I have to learn to like the hemoglobin? It's interesting. So what is especially interesting is this aesthetic problem of simplicity and complexity, which are fighting in my mind to be recognized, happens not only for molecules, but it also happens for structures which are 12 powers of 10, a million times larger than these. If you go up to these, for instance, you see structures. I could have shown you the Parthenon in Greece, but I show you the Taj Mahal at right, a high point of Islamic architecture in India. At upper right, a villa by Andrea Palladio. And at lower, this is a slide from your local cathedral. These are clear cases where simplicity is the primary aesthetic thing that's at work. But then I go somewhere else. I go to a typical Baroque structure. This is the Cathedral in Toledo in Spain. And there is a transparente, an incredible space going up from an altar to the cupola up above there. And that space is covered with sculptures in which, if any, there are no straight lines. There will be no straight lines. Any line that can be made curved, it will be. Any line that can be made complex will be. This is the aesthetics of hemoglobin being worked out in the... And both are beautiful in their own way. Similar things are at work here. One thing, I better get to talk about chemical bonds. So those lines in that molecule shaped like a football, in the morphine, those lines are chemical bonds. And I already told you that they are a little bit fuzzy. They are not rigid rods. That's just one model. But what are those lines? So it happens to be that this is what I do for a living. I try to describe them. But the important word is try here. It's a chemical bond is a connection that lasts for some time between two atoms, and its origins are in part classical, just from charges attracting each other, and in part quantum mechanical. What you see reproduced here is a kind of schematic from an Italian course about chemical bonding. So you can see that nothing is very simple here either. The nature of chemical bonds remains a subject of intense debate to this day. Earlier this year, I and two friends in January published an article with the title, "One Molecule, Two Atoms, Three Views, Four Bonds?" question mark. The question was whether there were four bonds in this, or were there three or two, more than one bond. And we incidentally had a good time here. We had a form of essentially a small play, a trialogue in here. Now, let's go back now to bonds again, but now in the context of reactions. So most of chemistry, or most everything I've told you about, not most of chemistry, what I've told you about is A plus B going to C plus D as the prototype of a chemical reaction. it happens that a lot of the time it's not as simple as that. Instead, what happens is A bonded to B, forming a chemical bond to B, a molecule, reacts with another molecule which has a bond between atoms C and D, and it goes to AC plus BD. Now, the first reaction is chemistry. The second reaction is a metaphor for a novel. And it was used as such by Wolfgang Goethe in 1808 in a novel called Die Wahlverwandtschaften in German. At right you see an illustration from that novel, and I bet you can predict what's going to happen in this. If you can't predict, then I can refer you to a Italian movie by the Taviani brothers from about 18 years ago or so, in which these things are spelled out much more explicitly, and there is a scene from that movie at the bottom. So that is about all that I have time to say about bonds. But I want to tell you about poetry. I have to leave chemistry for poetry. I have no regrets about doing this because poetry is important to all of us. Poetry penetrates in interesting ways to the essence of human existence. Poetry soars all around the tangible, in deep dark, in a world that we reveal and make. And so what I want to do is I want to, in a way that I took you through some chemistry, I want to take you through 3 poems of mine first. And fortunately, we have a translation of these 3 poems. About 10 of my poems have been translated into Italian. And I will read it in English, and I think the translator will read it in Italian, but you can look at it. The Bering Bridge. The old men say the sky was once so close that if you shot an arrow up, it would bounce back at you. The sky swallowed birds. Sometimes it lay like the luxuriating fog just above our tents, and a man could climb to the opening at the top when the smoke went out and talk to the gods. Then the redwoods came sacrificing all to the main trunk, and they jacked up the sky, and then men with balloons and telescopes pushed it back further, so it became difficult to talk straight to the gods. One had to yell or use the intercession of shamans. Now I have flown myself across the Pacific, seen the deep sky blue at 30,000 feet. They say a man has walked on the moon. They say the earth is getting warmer. I see smog, the sky coming back down over California. This was written in California. Now, this was translated by Renato Miradoli from Milano. I have written poems about my childhood, which was tied up with World War II. I was born in an unfortunate time in a happy Jewish family in southeast Poland just before World War II, and the years were difficult. Some of the poems I have described what I experienced or remember. I don't remember much. I was a child. But some of it I tried to imagine. And in this case, I tried to imagine the bond, and this is a different kind of bond now, a bond that formed between the inmates and the jailers, the guards at a concentration camp. Come, Mr. Gottlieb, you can do it, I know, and I did skin the others for this pink-cheeked German gentleman. For he had good reasons, barbed wire, and he did give me true instruction, the word, a manual. And he put in my hand the knife cut from an old ram's horn. Practice on deer if you like, he said. And there were deer in a fence, and the knife with the old letters carved in the bone slipped through the fat, sticking in just a few places. They taught me well. And he, well dressed, his shoes polished, stood on the side watching, and I knew he'd go on to ask me to skin myself. For him, I could learn even that. This was translated by Sylvie Coyot from Milano. And this slightly longer poem has some science. You notice the other two poems don't have too much science. There was a little science in the first one. The title is Rewrit, and you'll see in a moment what is being rewritten. When God made the sun, he lay back on his white sand beach, and reaching out with both pale hands into his space, he shaped there a sphere of hydrogen. God did set it alight with his nuclear fire. God felt its warmth on his soft hand, and it was good. It was his sun. When God set about next to make the moon, he put his feet on the ice cap of Mars and reached out again, seizing a piece of an old sun, and God threw it like a snowball at his earth. The earth rocked, and so the moon, God's moon, came to be. He felt its reflecting light, and it was good, his moon. When the time came for God to people this blue earth, he stood knee-deep in paddy and sea, and dear God, he didn't make people in his image, but just reached out his now sunburned hands to plant a mitochondrion, here a squid's eye, a seed of rice. Hazard, he gave them rules, God's time, and soon enough the creatures came, spoke, it was good, the word between God and his people. So you see here some of the themes that I write about. I write about nature, no different from other poets. I write about love, no different from other poets. I write about my experiences in World War II. Well, that is my own life. It took me a long time to start writing about that. And as I say, some of that is not real memory, for it is very hard. I was 7 years old when the war was finished, to remember. And it's hard for me to tell apart what I remember from what my mother told me. And part of it is just imagine, trying to think about that period. And here, I don't know, is this a religious poem that you just saw? Maybe. It's also a scientific poem, and I hope that the science comes naturally into this poem. Now, enough of me, and it's time to read a poem by a great Italian poet, and this is Salvatore Quasimodo's Mobile d'Astri e di Quiete, and I will not inflict my pronunciation on you, and so either the translator will read it or you will read it by yourself in the language that you know. There is an English translation, that's right. I think the music of the language is in his words, and the mysteries of poetry are also there. Many of his poems are in some way poems of loss, of mourning, but this one has both in it, and that's why, in part, why I chose it, because for the bond that forms. So what is that bond? The bond that is forming, and I hope that is true in my poems as well as in this much better one, the bond that is forming is between human beings through the poet. There is a difference between therapy and poetry. Poetry is written for other people. It may be therapeutic for the poet, but that's not the main purpose. A poet speaks to us, and if that experience shares some aspect of universality, and of course is tinged, touched by a certain uniqueness, then I think the poem works, as this one does. It has surprises, but yet we have known this feeling of stillness and quiet, and yet broken by a voice which brings some sweetness with it. The organizers of this conference gave a title for this lecture, which was Chimica e Poesia, Identici modi per creare un legame. And you may have noticed that I crossed out identical in the title when I started my lecture. Maybe you didn't notice, but maybe Saverio noticed. And the reason is that science and poetry are not identical. How could they be? How could they be identical? But they are within the same person, me. You saw my poems, you saw some of my chemistry, a little bit, not too much of my chemistry. I will talk at the university tomorrow about my chemistry. But you saw some chemistry. There are similarities and bonds. I tried to point them out, but there are differences. And I want to talk about a little bit about the same and not the same. So at the bottom you see this wonderful image of Caravaggio's Narcissus here, in which the mirror image is not Narcissus here. And we talk a little about the similarities and the differences. And I thought I would do that in a chemical context. So let me show you some molecules. Again, the convention here is that when you see a vertex of a polygon, you should put a carbon on there. And if there are, and you should add a certain number of hydrogens so that the total number of things bonded are 4 to that. So no hydrogens to that one hydrogen to that one, 2 hydrogens to that one, and 3 hydrogens to that. In each way, chemists are very simple. They know how to count up to 4, no more. So this is a convention just which allows chemists to show these molecules so that you can see the similarities and the differences. You remember that molecule of hemoglobin with the 9,500 atoms? That was a few thousand atoms too many for any human being to perceive the essence of the molecule. So you strip away the sum of the atoms to get at the essence. But sometimes you have to look at the atoms that you strip away. Here are 2 molecules, the chemical formulas of 2 molecules, which are, let me just tell you that all of the molecules that you see on this slide, if you had them in a powder, in a solid, which is what they are normally, though they're often dissolved in something, if you had them in a powder, they would all be white crystalline powders. of the 70 million compounds that chemists have made, 65 million are white crystalline powders. They include sugar, salt, penicillin, and saxotoxin, and a deadly neurotoxin which will kill you from one crystal of that white crystalline powder. If you're a chemist, you don't play Russian roulette with white crystalline powders by tasting them, because if you do not know, your body knows. So these are the same in external appearance, macroscopic, but now we want to look at their chemical structure. And they're similar in various ways. So what are they? Two of them are here, adrenaline and dopamine, are neurotransmitters, both. And adrenaline, you know, also as a hormone, which is what starts in period of immediate stress. It is generated in the body, a very important hormone. These are not only perfectly normal and useful, they're absolutely essential for life, these two molecules. You notice they're very similar. They both have this ring of 6 carbons and 2 OHs, and they both have something going off this way, except this, after there are 2 carbons and a nitrogen, 2 carbons and a nitrogen, but then this nitrogen has an extra carbon and this carbon has an OH on it. They're a little different. The body knows the difference. It does not generate dopamine when it should generate adrenaline. So it knows that. Now, down at lower left is a molecule called pseudoephedrine. Pseudoephedrine is not in the category of these molecules, but it's a harmless molecule which is used, and you can buy it in a pharmacy, as a decongestant. It is a medical drug of convenience, not of necessity, not life-saving. You might want to take this before an airplane trip if you are congested. And how does this differ from these? It doesn't have the OHs on the left that you see here. Over here, it's sort of the same, except it has one CH2 attached to a carbon rather over here, and it has this OH, but then adrenaline has that OH. So it's also similar. But pseudoephedrine is a real problem. The problem with pseudoephedrine is that by a simple chemical transformation, from it can be made an addictive drug called methamphetamine, called meth. What's the difference between these two? There's a model of that one over here. And you can see in the models the hydrogens, those are the white balls, 2 on this one and 1 each on each of the 5 here. Well, if you, I've circled here what the difference is between methamphetamine and pseudoephedrine. And the difference is that this has an OH and this has just 1 hydrogen over here, so that it's missing the oxygen. Now, that oxygen can be removed from this, which you can purchase cheaply, by a simple chemical process which can be done in a kitchen. Here is what happens in some kitchens when you try to do this at left. This is one of tens of thousands of home methamphetamine, not laboratories, illegal, small preparation things made very simply. If it weren't for the terrible human toll of addiction, we should be grateful for so much chemistry being done. But we're not grateful. This is the difference between the two is 1 atom. That 1 atom can be removed by a simple chemical process with chemicals that can be easily purchased. It is just that 1 atom. And this is part of this. By now, let me remind you of why I'm telling you this story. I'm telling you this story because this world is one of the same and not the same. These are things that are similar to each other and yet are different. And here I have another quotation, Primo Levi. This comes from a chapter in the periodic table called Potassium. What happens there is Primo Levi is tired of his chemistry. He is discouraged of studying analytical chemistry at the University of Turin, and he says, where are the theorems of chemistry? What he means is that chemistry is not like mathematics, and he sort of liked mathematics. Well, there are no theorems in chemistry. There only are likelinesses. Something is like another. So he goes over and works in a physics laboratory with a well-known physicist. And at some part of that work, he needs to wash out a glass vessel with sodium to remove some water from it, and instead he uses potassium. Well, he gets an explosion, and that's the end of this. This is his passage, and I'll let you read it again because we have it in Italian here. Primo Levi was a wonderful writer. Just like I am not a great poet, he was not a great chemist. But he was a wonderful writer. His career in chemistry is very interesting for a number of reasons, but I come now to the end of what I want to tell you. I've told you 2 words. So you have seen me talking here, and I put this up here so that we can see it. You have seen me talk about molecules, and you will notice that I have not given you a hagiography of chemistry. I have not told you about all the lives that chemistry has saved. It has saved many lives. I have told you about some molecules that make or have caused problems. The lead mining in ancient Sardinia, the methamphetamine. Some of my colleagues are not too happy with me. They would prefer hagiographies. They would prefer that I say only good things about chemistry. They think that the press is conspiring against us so that the word toxic becomes inseparable from the word chemical in an article in the press. Well, I do speak of these, and I am intent on showing you how little the molecules that heal are different from the molecules that hurt. And I also, that lead mined at such vast quantities in ancient Sardinia, it was made for good reasons. Not only to keep the Romans in good baths, but it kept the Roman Empire through the silver mines alive. So where is the bond here? Do you see a tie, a bond? Other people will tell you about distant galaxies and about quarks, the fundamental particles of matter. And those are very, very interesting. I want to know about them as much as you do. But I tell you, those quarks and those elementary particles will not hurt you, nor will they ever heal you. but molecules do, or have the potential of doing so. The same morphine that kills the pain is also addictive, not any different molecule. The reason I tell you this is that that's the real bond of molecules with humanity. That molecules, in a way, in that way, are like people. But for people, can also hurt you, and we know they can help you. We depend on it. No one is absolutely good. No one is absolutely evil. There is no question, whether it be molecules or human beings, what the direction for change should be. One should reduce the hurt and improve the healing. Of course, a person should be better. That's the ethical imperative. And that we both try to achieve this, both chemists and poets and people in general, that is our real bond. Thank you very much. Thank you. So we will take some questions, and the translator is going to come down here in a minute, and she will translate the questions from Italian into English, and vice versa. So please feel free to ask any questions that you wish. Just a moment while the translator comes. She's coming right away. Good. Yes. Hello. Yes. Thank you very much. She has worked very hard. Please give her a hand. Yes. Oh, if there are no questions, I will give another lecture of 1 hour. So you better ask questions. Tomorrow I will be at the university around 11 o'clock.
Domani sarò all'università alle 11, quindi se qualcuno...
And I perhaps will talk a little bit about some of my science, for what I hope is a mainly scientific audience.
E domani parlerò probabilmente di un po' della mia chimica, di quello che faccio come chimico.
Yes, there's...
Una domanda?
Yeah.
Io oggi ho conosciuto il professore, però non sapevo chi fosse. È venuto nella mia bottega e io mi sono avventurato in discorsi di chimica. Povero me.
Yes.
Francamente non lo conoscevo. E abbiamo parlato, per caso, di chimica, di arte e di evoluzione. Molto interessante il suo discorso. Complimenti. Grazie.
Thank you. Thank you. The speaker is a master goldsmith in your town who has taken a number of steps, Etruscan granulation. Maybe you can translate.
Il signore che ha parlato è un maestro orafo che ha studiato e ha fatto dei progressi, ha portato avanti l'arte etrusca della filigrana.
Well, there's one question there.
Volevo chiederle semplicemente che episodio, durante magari quali addirittura studi, è riuscita a trovare, ha sentito il bisogno di trovare un collegamento tra lo studio della chimica, quindi una scienza diciamo esatta, e la poesia che magari è meno esatta, almeno di quello che può apparire ai più.
Yeah, ask questions.
If you had an absurd situation in which you find a bond between chemistry, which is an exact science, and poetry, which is
Well, so there are similarities, there are differences. I will say a few sentences, then
Ci
stop.
sono delle cose in comune e delle cose che sono diverse.
Similarities are there in the fact, for instance, that a poem is often very concise, a very wonderfully original way of saying something. And chemistry or physics can also be very concise in a mathematical formula or in a chemical structure.
È una cosa che hanno in comune la chimica e la poesia, quella di dire in poche parole, in modo conciso, o un sentimento, oppure descrivere un fatto chimico in poco, dentro poche parole, dentro pochi numeri.
They both share a desire to communicate to other people, to speak to other people.
Entrambe sono accomunate dal fatto di parlare e comunicare alle persone.
There are differences. For instance, in science, one needs precise definitions. Until one could define what heat or work meant, one could not understand why the steam engines of the 19th century did not work with a high efficiency.
Ovviamente la scienza richiede un linguaggio più preciso, altrimenti non sarebbe stato possibile capire il funzionamento della macchina a vapore nel 1700.
But in poetry, that a word means several things, not one, and that it sound like 3, 4, 5 other words, that makes a poem richer.
E questo invece non accade in poesia, perché una poesia può contenere parole che sono scritte nello stesso modo, ma vogliono dire cose diverse, e oltre a questo possono anche richiamare dei suoni che a loro volta richiamano parole diverse, e questo è il fascino della poesia.
There is, in science also, one looks for universals, like equations that describe something. But in poetry, the path to the universal is through the observation of a specific object. It is this blade of grass that I see and this drop of dew on that blade of grass.
la scienza spesso ha bisogno di un linguaggio preciso e tende all'universale, quello che succede per un'equazione che intende proporre un concetto universale. In poesia invece ci si concentra sul minuscolo, ad esempio su un filo d'erba, e non soltanto su un filo d'erba ma anche sulla goccia di rugiada che si forma su questo filo d'erba. È una prospettiva completamente diversa.
But you asked for some absurd situation.
Lei mi ha chiesto di qualche situazione particolarmente
I'll
assurda.
tell you about an absurd situation. I went to a scientific lecture. The lecture was very boring. I fell asleep. Okay, good.
Ho partecipato a una conferenza e questo intervento era particolarmente noioso, quindi mi sono addormentato.
I woke up and the lecturer was still talking.
Sono svegliato e l'oratore stava ancora parlando.
So I stopped listening to the content and I listened to the words, how he was using scientific words.
E mi sono staccato dal significato di quello che stava dicendo, mi sono attaccato alle parole, a come le usava per parlare di cose scientifiche.
He was solving a mathematical equation, and there is something called boundary conditions, which you have for this mathematical equation. And what he said was, let us assume free boundaries.
Allora, stavo parlando di equazioni e in queste equazioni esistono quelle che si chiamano le boundary conditions, che sono, suppongo, prendetela, dei limiti di un'equazione.
He said, let us assume
Assumiamo, a un certo punto disse, diamo per certo che
free boundaries.
esistano dei confini liberi.
Yeah. I immediately wrote this down. There, he didn't realize it, but he gave me the beginning of a poem.
E lui non se n'è accorto, ma io l'ho scritta subito questa espressione, perché i confini liberi è una cosa
Because
stranissima.
how can boundaries be free?
È possibile avere un confine libero? E lui non lo sapeva, ma mi ha dato lo spunto per una
That's a
poesia.
poem,
E questa è
but
una
it was
poesia.
also a scientific equation.
È anche una questione scientifica.
Abbiamo un'altra domanda.
Più che domanda, sono rimasta affascinata dal fatto che io amo la chimica, ma sono rimasta affascinata dal fatto che i legami di cui lui parla fra atomi che poi compongono le molecole sono legami non statici, ma sono legami di vibrazioni. E allora probabilmente l'unione tra la chimica e la poesia è data dal fatto che le parole hanno una parola che può avere significati diversi e il discorso di cui sono fatte le parole assumono significato soltanto se vibrano dentro di noi e se risuonano in qualche modo dentro di noi. Credo, non so se anche per lei è così, se questo è ciò che unisce in qualche modo in maniera molto solida la chimica con la poesia.
I think that is very nicely said. I agree. It's part of that, part of the bond. I like the idea of the words vibrating in us.
Sì, in effetti è un'idea molto affascinante. Mi piace questo concetto delle parole che vibrano.
I like it.
Honestly.
Well, I think we have exhausted the questions.
Abbiamo esaurito le domande.
Thank you very much for coming.
Grazie per essere stati con noi.